Hey, today we're honored to invite Susan Athey to the Data Science Institute Distinguished Speaker Series. She is the Economics of Technology professor at Stanford Graduate School of Business, member of the National Academy of Science, and the receiver of John Bates Clark Medal. She has made fundamental contributions to a number of fields, to name a few: market design, auction theory, mechanism design, causal inference, econometrics, and machine learning. Today, she will speak of machine learning and the causal inference for personalization. Let's welcome Susan.
Thanks so much. I'm really delighted to be here. It's a big honor, and I'm a big admirer of everything that you all have going at Columbia and the Data Science Institute. It seems like a great organization, and I've enjoyed visiting in the past, and I hope to come back and see you all again before too long, once we all get our vaccines. So I'm going to be talking today about a set of papers, and some of them are actually joint with folks at Columbia, like David Bly. I'll be talking about that a little more at the end. And at the beginning, I'll be talking about some experiments our lab has been running around trying to use machine learning and personalization for various social impact objectives. So let me share my screen. All right, so somebody give a yell if that doesn't look good, and otherwise I will assume it does. And also I just wanted to encourage everybody, please type questions into the chat, and Mingzhang is gonna help interrupt me if the chat comes up, since I won't be watching it. But it's more interesting if you ask questions, so please do not be shy. As was mentioned, I'm at Stanford GSB. I'm the faculty director of an organization called the Golub Capital Social Impact Lab. And there we're partnering with various organizations to try to use all of our fun machine learning and tech toolkit techniques for social good. And some of the experiments I'll talk about today are done through the lab. And we have collaborators shown on this slide. So big picture, first of all, I know we'll have a broad audience today. In general, there's been the first, 10 years or so of this resurgence of machine learning and focus on supervised learning and so on was a lot of emphasis on prediction. While in more recent years, there's been an expanding interest in causal inference. And just to, really high level, why I think are people turning more and more to come back to a causal framework? Well, predictive machine learning models have a lot of great advantages, and they're general purpose technology. They can be used off the shelf and translated from one context to another without a lot of extra work. So that's great. But when you go in and try to really use them in practice, they are often lacking some desired properties. They might be uninterpretable. They might not be stable or not robust. There might be challenges with transferability. We have issues with fairness or discrimination, unintended consequences, and in general, an absence of sort of human-like characteristics of making reasonable decisions in never experienced situations. And in some sense, when all of the guns are pointed at predictive accuracy, you give up a lot, is a summary. In a causal inference framework, and that's really what we've been focused on mostly in empirical social sciences for the past few decades, generally your goal is to learn a model of how the world works. And in that setting, of course, you can have still a lot of variation in how what impact of interventions, like an intervention might work better in a rural village, but not as well in a big city or vice versa. So the impact of interventions can be context specific, but still your goal is to understand how the world works. There's a model that maps context and interventions to outcomes, and there's a formal language in that model to separate correlation from causation. Now, whether you can actually implement on that, whether you have data that actually allows you to accurately estimate the parameters of that model is another question, and it's a that's one of the main things we grapple with in social sciences. But that's really the stated goal. We want to understand how the world works, and if you do understand the way the world works, you can do counterfactuals. You can say, well, what would happen if we change this, if we change that? What would happen if I raise prices, change the minimum wage, change immigration policy, two firms merged? These are all the kinds of things you can do if you understand, have a model of how the world works. So the ideal causal model is by definition stable and interpretable. It's transferable to a new context distribution. And also a lot of questions around fairness actually relate to correlation versus causation. Your performance might depend on physical and mental ability or psychological factors like risk-taking. And those are the fundamental concepts, not necessarily gender or race. They may be correlated with factors that shift those distributions, or people might have insufficient access to education that helps with performance. But there's typically relatively limited direct causal effects. And so really having a model of the world helps you sort out a lot of these questions. So I'm not going to solve all the world's problems about causal inference in this talk, but just to say that this is kind of a motivation why there's getting to be, I think, more and more interest, because when you go and practice to use machine learning, especially in businesses and governments, a lot of times you're actually asking questions about intervention, and prediction is just a means to an end, but it's not the end goal. Just to give a few examples of this, this is a paper that I worked on with David Bly and one of his then postdocs, Francisco Ruiz, when he was at Columbia. And here we were looking at restaurants, and we used mobile location data to build a model of what factors lead consumers to choose different restaurants as a function of travel time and the restaurant characteristics. And if we can contrast sort of counterfactual questions with predictive questions in this example, the kinds of questions we were interested in were questions like, what would happen if I opened a new restaurant of a given cuisine type in a new location? And who would the restaurant steal customers from if counterfactually a new restaurant opened up in a particular place? Where a predictive model might just ask, given the restaurant characteristics and the existing distribution of restaurant locations, what's the best prediction of foot traffic? So we see the picture is showing what we think the best restaurant category for locations would be. And it looks like Vietnamese would be well suited for South San Jose, for example, while Chinese is more suited for close to San Francisco. But if I was just building a predictive model, I might not really care whether a restaurant is giving traffic because it's Chinese or because it's close to San Francisco or some combination of the two. I just want to predict foot traffic. And if it's the case that in the data, most of the Chinese restaurants are close to San Francisco, it doesn't really matter whether I get them right or wrong. But from a counterfactual perspective, I might want to say, well, what happens if I plopped down a Chinese restaurant in South San Jose? And what would happen, and who would it steal customers from? So those are sort of the difference between the questions. Another example of where sorting these out can be important, or an example where it's useful to distinguish is I've done a lot of work with David on supermarket purchasing. And one thing you see in the data is that diapers and coffee are positively correlated. So on a shopping trip that has coffee, you're also more likely to have diapers than on a shopping trip that doesn't have coffee. So there's a difference between a predictive model. So suppose I had data about whether or not you bought coffee and I wanted to predict whether you bought diapers. It wouldn't really matter why this was the case. I could just say, well, okay, coffee predicts diapers. And that's a good point. But if we were trying to think about a supermarket setting prices, it matters why the two of them go together. We would care what happens to purchases of diapers when the price of coffee changes. So, if we think about running an experiment where we increase the price of coffee randomly, we can think, what is the effect on diaper purchases? So when coffee is more expensive, you buy more diapers. That means diapers and coffee are substitutes. If you increase the price of coffee and you buy less coffee and less diapers, that's like coffee and diapers are complements. They go together. You can't have your diapers without your coffee. And if raising the price of coffee doesn't affect diaper purchases, they're independent. So in the independent case, where you might think you need the same number of diapers no matter how much coffee you drink, the positive correlation in the data is explained by correlated preferences. The same people who are sleep deprived also change a lot of diapers. But when you think about decisions by the firms, there's actually two different timescales you might think about. If you are trying to get a coupon to get people to go to the store, a coffee coupon might actually attract people to the store who buy more coffee and more diapers. And so then actually it may not matter so much why they go together. It's just all you care about is that the coffee coupon gets people to the store who's going to sell you diapers. But if you think about a price change that the consumers would encounter once in the store, once you're in the store, a change in the price of coffee may not affect how much diapers you purchase. So it's really important to have a clear model of what's going on, what the data generating process is, and what decisions you're making and on what time scale to know what's important to learn from the data. And again, this is something that social scientists put a lot of emphasis on, understanding the data generating process so that you know what are the important concepts and then can think about how you might estimate them. Okay, so in terms of like some of the big challenges for doing this, there's really two big challenges for estimation of quantities that are used for counterfactual inference. The first category relates to prediction versus causal inference. A huge challenge is the availability of experimental or quasi-experimental variation in the data that just allows you to separate correlation from causal effects. And so one big answer to this, and this is the answer tech firms have, as well as scholars in social sciences that have started going out and running large experiments, like the Green et al. Get out the vote experiments, and voter mobilization, whether it's online or offline. I'll be talking about some experiments our lab has run as well. And of course, tech firms run a ton of randomized experiments. So you run randomized experiments and then you have experimental variation and you can separate correlation from causation relatively easily. But even if you have that kind of experimental variation in the data, a second problem is actually customizing machine learning optimization for estimating causal effects and counterfactuals of interest. And that's something that I worked on a lot in the early 2010s and continue to work on. And I'll show you some of those solutions. A second big problem is statistical power. Historical observational data may not be informative about causal effects, especially if there wasn't good randomized or quasi-randomized variation in your treatments. But then if you design an experiment, you're often limited in your sample size. And it may also be hard to design a large enough experiment. And then second, if you work with a company that has data or has a large customer base, it's often the case that your treatment effect sizes are small because the firms already are doing pretty reasonable things. So you're less likely to parachute in with some very large treatment effect. And finally, personalization is hard. You just never have enough data. So if I'm trying to find someone, exactly like you're unique. And if you're described by a large number of characteristics, even if I observe them all, I don't have enough people who are just like you to really understand whether the treatment works for you. And that contributes to that statistical power. So it really matters to be careful and to use very and very fine-tuned methods for estimating causal effects and personalization as a result. And just to kind of formalize this idea about trying to find the right objectives and to sort of think about prediction versus causal inference, for prediction, you see the ground truth in the test set. So if I build a model to predict mu hat of X, X is your observable characteristics, mu hat is an estimate of the conditional mean, I can think about optimizing a squared error loss, which is my prediction, minus an observed outcome. And so I can just take a test set, and that observable loss is that a squared error loss is observable observation by observation in a test set. Whereas for treatment effects, people are not walking around with a treatment effect stamped on their forehead. A treatment effect is the difference between two counterfactual outcomes. There's me with a vaccine and me without a vaccine, but you don't see me with and without a vaccine at the same time. So you don't know my treatment effect. individually. It's never observed. It's infeasible. The squared error loss for treatment effects is infeasible. But it's important to optimize for the right objective because the factors that predict outcomes may be different than the factors that lead to heterogeneous treatment effects. We know that older people die more often from COVID, but we don't know whether the vaccine, say we just had this thing with AstraZeneca, we don't know whether the vaccine is more or less effective on old people just because they die more often. Age could be an important factor for heterogeneous treatment effects, or it might not be. There might be other factors that are more important. So this is so optimizing for the right objective is important, especially in an environment with scarce data. So this is something I started grappling with, as I said, in the early 2010s. I had a paper with Hito Mbens where we proposed a couple of different alternatives for either trying to come up with an unbiased estimator of a squared error loss, or transforming the outcome in a way that you can actually transform this into a prediction problem and just apply off-the-shelf prediction methods. And that's also been extended by other authors as well. Then a team from Berkeley, as well as my co-author Stefan Wager with another co-author, proposed some alternatives. They called XLearner and RLearner. And so there's basically a whole literature coming up with objectives that you can use both to optimize and evaluate performance of causal inference methods. One big point, though, is that while you can break out prediction observation by observation in general to evaluate, causal effects out of sample and try to see how well calibrated they are, you do need to be able to do some averages or put things into groups. And I'll show you how we do that. Okay, so let me pause there. Or if there's any questions, please feel free to type them in the chat, or I'll pause for a second if you want to speak and unmute. Okay, let me jump in now, and I'll spend the rest of the talk going through some applications, and we'll see how far we get. And feel free to stop me and interrupt me. So let me start by looking at randomized experiments we've been running. And so I guess, there's some, by the way, I should have mentioned earlier, there are many different types of questions within causal inference. In my lab, we focus mostly on estimation and applying different kinds of estimation methods to different types of design settings, different ways that treatments are assigned, and different kinds of models. So some people might think that, oh, well, if you have a randomized experiment, like what other problem is there? Like you've solved the causal inference problem. You've solved the identification problem. That is, that if you had enough randomized data, you could eventually answer questions about causal effects. But the estimation problem, coming up with good estimates, is still challenging, especially when there's problems of statistical power. So, when we think about heterogeneous treatment effects, in the literature on randomized experiments in social sciences, we've traditionally tried to avoid data mining. And data mining was actually a bad word, and it's also can be thought of as p-value hacking is the reason it's thought of as a bad word. So the idea was that historically, theory or intuition would tell us hypotheses. We would tell everybody ahead of time what hypotheses we wanted to test, and then we would report the answers to those afterwards. And that would protect us from just searching in the data. And if you think about like a pharmaceutical case, right? If a pharmaceutical company spent a lot of money and effort developing a drug, if they were just allowed to look and look and look for different subgroups until they found that, well, this drug works for people between 30 and 35 who, have this pre-existing condition or are men, there's going to be, if you test lots of subgroups, you'll eventually find one where the drug works. And researchers have an incentive to publish, just like pharmaceutical companies have an incentive to get their drugs approved. So there would be a lot of temptation to just keep looking until you find something where the thing works, and then ex post come up with some justification for it. And so we try to tie our hands against doing that. And in fact, there's been a bit of a crisis in reproducibility in science around that. But on the other hand, sometimes you don't have hypotheses in advance. And it's really crazy to say, well, like, we're not going to use the data to figure out for whom our drug works. Like, that seems like a really big limiting factor. And so one of the goals of my research in this area has been to come up with data-driven approaches that allow you to use the data to search for heterogeneity, but at the same time, protect you and still be able to give valid confidence intervals out the other side. So I'll show you how we did this in an experiment we ran in collaboration with a fintech company. Here, the research questions were how to increase the quantity of micro giving, trying to give small amounts of donations. And we want to see whether appeals about the impact of a charity work. And in the big picture, if telling consumers about impact makes them give more, then that could also encourage charities to be more impactful, and it could try to allocate money to the best charities. So that's a long-term goal. But here we just want to see what kind of impact appeals actually drive consumer response. So what we did is we're as consumers check out with this large fintech company, we are giving them an opportunity to donate $1 to support a charity name. And then the variations will be around the information that we give them. So the second line of information here in this slide is what we're going to vary in the experiments. And so we worked with two different charities, Evidence Action and TechnoServe. And this slide shows what the different informational lines were. So the control is there's no information line. And then we have an activity. The activity line just says, what do these charities do? We then have a treatment where we validate them with stars. This was rated 5 out of 5 stars by a charity rating group. Another treatment is we say what the cost per outcome is. $1 provides 2 people with free and reliable access to safe water for the year. And then we have various combinations of those. Activity plus validation, whether or not we have the stars or no stars, and the cost per outcome with or without stars. So those are the treatments, and we're going to, in this experiment, we only run it on 2 charities. It turns out the results are pretty similar across the 2 charities, so I'll just show you pooled results in the interest of time today. So when we run this experiment, we've got, and this is a reasonably large scale experiment. So we have several 100,000 people in some of the treatment groups, and here we are showing what the donation rates are for those different groups. Now, when I said earlier that it's actually, you need a lot of data sometimes to come up with treatment effects and heterogeneous treatment effects, the overall donation rates are low. They're less than 1% of people donate on average. So you do need a lot of data to start to be able to tease things out. What we see is that cost per outcome information performs the best overall. And we also actually see that more information is not strictly better. So this was a shorter script with less information in it. Now we'll go to look at heterogeneous treatment effects. So to think about our approach, what we're going to do is we're first going to use methods that I've developed with a variety of co-authors that estimate heterogeneous treatment effects as a function of observable characteristics. Those are called conditional average treatment effects. That is the expected value of a treatment effect conditional on your characteristics, the key. And so we're going to estimate conditional average treatment effects using machine learning algorithms, and specifically my generalized random forest package that is developed with Stefan Wager and Julie Tibshirani. And you can check out that package it's an R package, and it's fairly well developed and efficient. If you haven't tried it yet, please go check it out. We then use the estimates of the conditional average treatment effects to create subgroups based on the predicted treatment effect strength. So for example, we'll put people into quartiles, the top quartile of estimated treatment effects according to their characteristics. We'll then describe how those groups differ by comparing their group characteristics. And I would say this is an important difference. A lot of random forest packages look at things like variable importance, just like how often you split. But a key insight that we think about a lot in social sciences is that, if 2 covariates are highly correlated, it's kind of arbitrary which one you put in a model. And so variable importance might not really pick things up. So here, we're just going to describe the groups according to their characteristics. It's possible that the forests and trees didn't even split on a characteristic, but still that characteristic differs across groups. And that's, I think, a more theoretically justified way to think about the heterogeneity across groups and something like variable importance. And then finally, we'll look at estimating optimal policies and see whether personalization is worthwhile. So when we, and just looking back at this chart, we can see that the cost per outcome and cost per outcome with plus validation with stars are pretty similar to one another. And so there's some chance that one of these is better for some groups and another is better for other groups. But it's also possible that the same treatment is best for everybody. And so those are the kinds of questions we're going to be asking. And often for a company, implementing personalization is costly. So we might want to know whether the personalization is sufficiently strong to be justified. Another thing we might look at is that we might not have validation information or cost per outcome for all charities. So we might want to restrict the treatments to ones that don't have the cost per outcome. And then we might say compare between activity and activity with validation stars, but without the cost per outcome measure. So our first look here is we've divided into quartiles according to estimated treatment effects. And here, just for simplicity, we're comparing the cost per outcome plus validation against the cost per outcome only to see which one is better. And we see that for 3 of the quartiles, just the plain cost per outcome treatment works better. And for the lowest quartile, we see the cost per outcome plus validation works. Another thing that's kind of interesting, so we've shown not just the treatment effect, but the treatment and control group separately. In the middle buckets, the overall donation rates are low, while the donation rates, the baseline donation rates are actually, higher on the first and last quartiles. And so that's sort of suggesting that if for people who don't donate very much, it doesn't really matter, but we actually are seeing opposite treatments being good among people who actually donate a lot. I'm not going to go into the details for interest of time, but on the right, this kind of just shows how we want to compare the characteristics of the different groups. And on the rows here, we have characteristics of the individuals, and in the columns, we have the quartiles of estimated treatment effects. And so we see, for example, that prior donor status is higher in the fourth group and in the first group, and it's very low in the middle, and especially the second group. And so that's basically saying that people who have donated in the past either have low treatment effects or high treatment effects overall. And then we also see some other patterns in terms of people's engagement overall, how much they spend on the web is another characteristic that differs across these different groups. So this is basically, I should also mention that, what I'm showing you here on the left, we have data from a test set. So we've used data to put people into groups, but then the same data is not used to put people into groups and evaluate treatment effects. So the treatment effects we're showing are sort of model free. And they're so we use the model to put people into groups, but the estimates, the magnitudes of the treatment effect are not dependent on modeling assumptions. The next thing we do is go to think about estimating optimal policies. And so a policy is a rule or a method by which we decide who is targeted. So it's a function mapping from covariates to treatment assignments. Now, understanding heterogeneous treatment effects helps us assign an optimal policy, of course. So people with high treatment effects, you'll want to treat, and people with low treatment effects, you don't want to treat. I should mention, though, that in many experiments, you can have heterogeneous treatment effects without being able to find a benefit to personalization, because you could have, like, vaccines could work well for everybody, better than nothing, but it could be relatively better for some groups than others. That's pretty common. But it's less common to say that, vaccine A is better for one group and vaccine B is better for another group. That's a much harder thing to find, requires more power. And of course, there may not be any groups that shouldn't get a vaccine at all. And often when we go out and run experiments or try treatments, we try beneficial treatments. And so it's less common to find experiments where people have run where the treatment is actually bad. So that's it's much more common to find heterogeneous treatment effects than it is to find statistically significant benefits to personalization. And one of the learnings I have is that if you're looking for that, you may really need to actively design an experiment that's targeted at that. Because if you just design a generic experiment, you're going to design something that works well for everybody. Where if you think this is going to work really well for liberals and this other thing's going to work really well for conservatives, unless you're planning to target, you wouldn't want to run an experiment with something that's going to alienate a big chunk of your population. So this is what a treatment assignment policy might look like, just to be concrete. So we might say if people have donated less than $25, that would be the true branch of the tree. And if their prior spending was less than $1,000 in the true branch of the tree, we might assign them to the cost per outcome plus validation with stars, and so on the basis of this decision tree. We have a policy tree, R package, that goes alongside our GRF package that allows you to estimate simple trees like that using experimental or observational data. It could be instrumental variables, it could be unconfoundedness, or it could be randomized experiments. And the package also works for multiple treatment arms, which is actually a pretty hard computational problem. So you can check out our package if you're interested in trying that out. And we have theoretical papers published in a couple different journals around this, and more work in progress. Just to see how this looks and how you would actually think about evaluating the impact of a policy, it sounds really complicated to estimate a personalized treatment assignment policy, but it's actually fairly simple to evaluate how they work. So just to see that, on the left, I've got a little picture of data from the experiment. The covariates X1 and X2 are on the X and Y axis. And the circles are things that in our observed data were assigned to control. The squares were assigned to treatment. So this blue is our raw data that we're using to estimate and evaluate treatment assignment policies. Now, if I split my data into train and test, and I take training data and I estimate, say, a causal forest, that would allow me for every individual to estimate their individualized conditional average treatment effect. Based on that, I might assign people with positive treatment effects to a treatment group, and I might assign people who have negative treatment effects to the control group in a counterfactual policy. So now I've colored red people that counterfactually I would like to assign to a treatment group, and I've colored green counterfactually the people I would like to assign to the control group. But in a test set, I can evaluate very, very easily the impact of this personalized policy. The policy itself might be complicated. There might be different regions, it might be nonlinear. The policy itself is complicated, but in the end, to evaluate its effectiveness, all I need to do is, let's look at the people who were colored red and the people who were colored green. And I have actually two groups now, one that's assigned to treatment and one that's assigned to control. Now, within each of those groups, as long as there's overlap in my original data, that for each set of characteristics, we actually do have both treated and control in the actual data, then all I have to do is take these red observations and just take the difference in sample means. I can just take the average treated guys and compare them to the average control guys, that is the average of the circles and the average of the squares among the red people. And that's going to give me, in a test set, if I had random assignment, that'll give me an unbiased estimate of the average treatment effect for the people I counterfactually assigned to treatment. While if I just, in a randomized experiment, I could just take the difference in sample means between the green circles and the green squares, and that's my estimated treatment effect for the people I assigned to control. So if I did a good job in estimating my policy, then I would hope that the treatment effect is negative for the people I assigned to green, because those are the people I'm withholding the treatment from. And I would hope that the treatment effect is positive for the people I assigned to red. So I use some data to color them green and red, and then I use a different data set to evaluate whether I actually did a good job. And then if I did a good job, without any model dependence, I can evaluate how good a job I did and what the gains to using this counterfactual policy would be. This is called off-policy evaluation. I know this all seems really simple, but actually it gets kind of confusing. But it is actually simple once you think about it. And then there's a choice of whether you use a simple policy or a complex policy. So the forest might be nonlinear, and adjacent, close by observations in X space might not get the same counterfactual treatment assignment. Well, if we use something like a tree policy, it'll be a simpler assignment rule, and it'll be simpler to describe, and we'll have some discontinuities, obviously, when you leave the boundary, but generally nearby observations will have the same counterfactual treatment assignment. So and we have found in practice that in some cases the simpler things work better, and in some cases the forest policies work better. It just depends on the data generating process and the structure of the heterogeneity. So just to see how this works in the charitable giving case, we'll have some covariates like age and income. We're going to use the causal forest to do a counterfactual assignment model. Then we're going to assign people to different scripts. And then we'll look back in our test data for each of the groups that are counterfactually assigned to different treatments. We can compare the outcomes from that we actually see in the observed data to see how well that personalization did. So our policy tree will put out a little table like this, and I'll show on the left how that works. So in this case, for illustration, we're using the cost per outcome plus validation with stars as the baseline. We're saying if that was our baseline, what would be the benefits from selectively assigning people to other treatments? So in this case, we would assign 53% of people to the cost per outcome treatment and 12% of the people to the cost per outcome plus validation. And then we can see what is the benefit in terms of donations relative to the baseline where they all got cost per outcome plus validation with stars. And here we see that's statistically significant. Now, I'm showing you this actually, this is very much work in progress and this is tentative. So I showed you this so I can illustrate how this works. In fact, the cost per outcome is the best uniform script, and we're getting somewhat conflicting and unstable results as to whether personalization is actually better than the best uniform treatment. So I'm presenting you this base case, even though it's not going to be our final result, just so you can see how it all works, and it looks pretty on the slide. But ultimately, stay tuned and we'll have sort of final results hopefully soon. We're working on writing all of this up right now. And then we do a similar thing for evidence action. And so we basically, on the right here, we can look at the characteristics of the groups. So the people assigned to cost per outcome plus validation had a larger days since last transaction than the people assigned to some of the other groups. And we can see how the groups assigned to different treatment arms differ. Okay. All right. So then that's it for the charitable giving, but that kind of shows you how you walk through the whole enterprise. Here we ran an experiment. We put people into groups by their treatment effects. We estimated optimal treatment assignment policies, and then we evaluated using test data how much benefit there was to personalization. Now let me show you a different related experiment, and I'll show you a nice little picture we can draw. And here we're also going to highlight the difference between prediction and causal inference in terms of targeting. So this was a collaboration between the City University of New York and Ideas 42 and our lab. And here we were also looking at nudge experiments where we're trying to target those. So this was an experiment run in 2017 and 2018 where they were trying to get students to apply for federal financial aid. Eligible students were matriculated students who hadn't yet renewed FAFSA, their federal financial aid forms, in February of the study year. And one of the key things is some of these people had actually dropped out, but they might still come back the next year. And so whether they were currently enrolled turns out to be an important variable. But just to say that you can be interested in applying for financial aid for the next year, even if you're not currently enrolled. And we had overall both experiments in both years about 65,000 students in the experiment. And so what they were getting were text messages that basically nudged them to fill out these financial aid forms. One of the things that we do, and I also could have showed you this in our last experiment, we try to look and see how correlated are our estimates of causal effects with the actual practice. And this is, again, it's a tricky thing to do, a calibration regression, but it requires transforming the outcome because we don't actually observe treatment effects for any individual. But that's one of the things that my work and others like Chernozikov et al. have highlighted ways to do that. And so what we see here is that we're sort of calibrated in that, a higher predicted treatment effect corresponds to about 0.5 of an actual, but we're not perfectly calibrated. And this is kind of a noisy experiment, it turns out. And we can see that in this picture as well. We put people into groups according to their estimated treatment effects. What you would like to see is a nice upward slope where each of these groups is statistically significantly different from the others. And here we're not really seeing that very well. We're able to identify sort of a low treatment effect group in 2017, but we can't really distinguish the top quartiles very well. And so this is basically saying there's a lot of noise and we don't really have good signal for heterogeneous treatment effects. And I should say this is a very common pictures. I've run these on lots of experiments, and it's pretty common not to have enough power to get heterogeneous treatment effects out of these experiments. So if you simplify things and though look at the most important variable driving this when we look at the data is whether the students were enrolled. And if we just separate by whether students were enrolled at the time or not, we find that students who were enrolled had higher treatment effects. I should say that's not obvious because you might think that, people who are enrolled are kind of with it and they're going to be filling out their financial aid forms, while people who have dropped out really need to be reminded. So it's not completely obvious that that would be the case, but that's what we find, that students who are enrolled are more amenable to the text messages. So in this final picture, there's a lot going on in this picture. What we do is we compare the benefits of targeting students for these messages according to different types of models. So one thing we do is we target, imagine what happens if we counterfactually target people by their conditional average treatment effect. And that's kind of this olive line in the picture. So just to explain the olive line, we look at the percent treated on the x-axis. And on the y-axis, we estimate the benefit of that policy. So you can see the pink line is kind of a baseline where we randomly assign people to get the text messages. Because the text messages are good, if you randomly assign them, that's going to be linear because every additional person that gets a text message is going to be another increase in the likelihood of people filling out their financial aid forms. And at the far right, that's the benefit if everybody gets the text messages. But the text messages might be expensive, so we might not be able to target everybody. If we can see that the olive line is significantly better than the pink line, which basically means that generally targeting people by their conditional average treatment effect first is going to give us better results than just targeting first randomly. But in some places, the olive line is pretty close to the pink line, which is saying that, actually we can't really tell very well in that region who's the best person to get the treatment. Then we can see another interesting line is this red line. We're looking at where we're looking at, I'm sorry, let me talk through the red line first. So the red line is basically targeting versus a prediction of outcomes absent the treatment. So the red line is like a prediction model where we're just predicting who was likely to fill out this form. And so if we look at the if we look at these numbers and compare them, what we find is that that would be a very bad way to target. On the other hand, if we target people by their enrollment status, that does about as well as targeting by conditional average treatment effects. So if we target people who are already enrolled, that's basically capturing most of what's going on with the conditional average treatment effects. So in this case, you didn't need a complicated model to target. You could have just targeted based on one thing. But even better would be to target people on the probability of filing. And so what we find is that actually targeting people who are already likely to file is the most effective thing. And targeting people whose baseline probability of filing was low is bad. So the nudges were most effective on those likely to complete anyways, getting them over the finish line. And this is showing that up front, maybe you would think that the people who are most likely to forget are the ones who might be most benefiting from the nudge. But it turns out the people least likely to forget were ones that were most likely to benefit. And so we, by understanding and analyzing the conditional average treatment effects and evaluating different doing off-policy evaluation, we're able to understand which works best. So finally, I'm going to skip over some of the math. I'm going to talk about some work that I did with David on shopping. And in this case, we're trying to estimate people's responsiveness to price changes. And so let me jump right to the off-policy evaluation part, because that's the part that sort of connects with what else we've done. So in this case, we had data from supermarkets. There was not actually random assignment of prices, but the supermarket was changing prices every night at midnight on Tuesday to Wednesday. And it turns out Tuesday to Wednesday are very similar shopping days and all their other characteristics. And so what we do is we control for holidays and other kinds of general time trends, and then look at the person shopping on whether they came on Tuesday or Wednesday as if that was random. And we do a bunch of checks in our paper that show that that works out. And so here, in order to look at off-policy evaluation, what we did is we used a model to estimate price sensitivity, and we estimated a personalized model of price sensitivity. And we used that to put people into individual customers into groups. And so we put them into groups according to whether they were the least price sensitive, the middle price sensitive, or the most price sensitive. And the way that economists write these things, they have these demand curves where they have prices on the y-axis and quantities on the x-axis. So we've plotted it that way to be familiar to economists. And what we see is that the people, these pale peach people that we identified as being least elastic, that means the least price sensitive, in a test set data are the least responsive to price changes. So what we did is we held out test data, and then we compared the total quantity sold on Tuesday to Wednesday for the group of people that we had classified as not price sensitive. And that's this, say, the peach thing. So on days where there was a more than 25% price decrease from Tuesday to Wednesday, there was a small increase from Tuesday to Wednesday of the purchases for this least elastic group. But the group that we've classified to be most price sensitive in the held out test data, there was a large increase in demand from Tuesday to Wednesday in the held out test data. And so we have a complicated Bayesian model, and it's using all of the beautiful estimation techniques that's been developed in David's lab for using variational inference and matrix factorization to come up with these personalized estimates for these people. But that can be, from the evaluation perspective, that's sort of a black box. We just use this. It's, of course, that model was finely tuned to optimize for price sensitivity coefficients, and that's a big point of the papers. But to evaluate its performance, we can do that in a model-free way on a test set. In this held out data, all I'm using is which group the people were assigned to. And I look at days with these price changes, and I can see how well it works. In an ongoing paper, we're looking at also the value of information from having larger and bigger and smaller data sets, like the value of retaining data longer, having more stores, more consumers, and so on. But again, we do this off-policy evaluation. And just to kind of dive in a little bit more on how the off-policy evaluation works, we can imagine that in the actual data, the price was high for a while, then low, then high, then low, then high. So this is the top bars as a function of time, say the prices that consumers experienced. And then we have users, and the users show up at the store on different dates. And for the purposes of this discussion, let's imagine that's randomly assigned. In the data, we actually do more things to adjust for factors that might affect them to come on different days, but let's just imagine this was randomly assigned, which day the consumer showed up. So user one might have showed up once on a low day and once on a high day. And then our model might say, that consumer should actually be assigned a high price. Well, say users 5 and 6, we think they should get a coupon based on their price sensitivity. Okay. So if based on those assignments, I'm going to color orange the top 4 consumers because I want to counterfactually assign them to high. Green, the users 5 and 6, I will counterfactually assign to get a coupon. Then, in order to assess whether this counterfactual policy works well, I look out at my data and I can compare. I can look at how many were sold on the high days versus the low days, and I can see whether, based on for this group, these green users, I can see how much was gained by giving those people a coupon. Then I can look at my orange users and see historically in the data how much was gained by giving those users a coupon or cutting their price. And hopefully, if I've done my job well, you get more revenue from giving the green users a coupon than from giving the orange users a coupon. So our model is used for the assignment, but then in a model-free way, I'm able to evaluate how well my assignment works. And this is just the same idea as before. Now it's just applied in a different context. And so what we find in this case is that our model says that you get an 8% gain in revenue from targeting coupons versus randomly assigning them. And in our test set, so if we took our model seriously, that's what the model would say. But when we do this model-free test set evaluation, we actually get a slightly larger benefit from targeting, which is great. Although the fact that it's higher is probably mostly sampling variation. So just to wrap up, in what we're doing here is we're doing counterfactual inference, and that differs from prediction. We can do things like learning the parameters of a utility from revealed preference and then predict responses in alternative situations, like with alternative couponing policies or alternative treatments. We need to find data sets or run experiments that are large enough and have sufficient variation to isolate causal effects. And also they have to be big enough to assess the credibility of your strategy. And we should be selecting counterfactuals where it's possible to assess and validate them before we charge off and do more stuff, taking our model too seriously. For evaluating the value of personalized targeting, not all data is created equal. It's going to actually vary with the setting quite a bit. And in many cases, it's pretty hard to find benefits of targeting at all. It's more commonly going to be the case if you've actually designed your experiments to do so. All right, so why don't sorry, I ran over a minute or two. Let me stop there and take questions. Thank you.
Thanks, Susan, for the wonderful talk. Here there are 2 questions in the Q&A session. The one is, how can we use the causal inference to detect a hidden bias, say in the jury selection?
Yeah, so I mean, that's a big question. So basically, I think the way that causal inference would fit into things like bias and fairness is that you need to start by writing down your data generating process. And you can write that down as equations. You can write it down with boxes and arrows. But however you choose to write it down, you need to write down the way that the data is generated and what you think what you think should matter or shouldn't matter to even define what it means to be fair. And once you start writing things down, you realize that actually there's lots of different ways you could define bias and Fairness. So I guess I would say that the thing that's at the root of all of these is writing down a clear data generating process. So, and then there's a question about Pearl's methods. So basically, the thing that's, and a bunch of people have written, writing down things in equations or in terms of boxes and arrows is something that I think everybody in working causal inference agrees on, that you need to write down your data generating process and specify your assumptions clearly. There's been a lot of discussion about, well, there's some things that you can't do with boxes and arrows because there's assumptions that can't be expressed that way, assumptions about monotonicity, things about magnitudes can be hard to express that way. On the other hand, if you have some things that are very complicated with a lot of moving parts, the equations can be overwhelming and not very intuitive. So, using boxes and arrows is can be a more visually appealing and intuitive way to look at things. So I think that really just depends on the context, which one you find more useful. I think economists have we've always used diagrams when things are complicated especially in presentations to help make sure people can see things when the equations get complicated. But in other cases, the equations are important. And so for things like auctions, it's hard to do them without equations, or things like inferring a firm's cost from their pricing decisions, you kind of need the equations. So those are just two different ways but I think we all agree that you want to write down your data generating process and be very clear about your assumptions. There's also different strands of literature. So as I tried to mention in the talk, a lot of social scientists, or just generally practitioners, you care about the magnitudes. You want to do a good job estimating magnitudes. You're not as interested in the philosophy. You want to get the numbers right. And so there's a lot of emphasis on measurement in social sciences and making sure your magnitudes are correct. And it's often really hard to find just one causal effect. Well, if you have a complicated physical or biological system or a software system, it makes sense that you might actually want to discover what causes what, and you might have some hope that the data could help you figure out what causes what. While, if I'm trying to understand the impact of education on somebody's labor market outcomes, I know that flow. I know it's education causing their labor market outcomes. My problem is, how can I separate correlation from causation in the data? It's all about estimation and finding the right quasi-experimental data. So I think these schools of thought have tended to emphasize different things, different kinds of applications, just because their audiences are interested in different questions, but there's also a lot of common ground. How large is large enough in terms of the data sets? To use machine learning, you pay a price for adaptivity. You pay a price for letting the data figure stuff out. If you want to use the same data to figure out what the functional form should be and estimate your effects, you need, one way or another, you need to make yourself safe from using the same data observation to choose your model and to estimate effects. That's never safe. There's always going to be a price to be paid for that. So you need to have enough data that sample splitting and doing some holding out in some way or another works. If you know the structure, it's always better to put it in. Just letting the model figure it out is a waste of data. If you already know something about the structure and the data generating process, you should always incorporate that manually. And then use up your degrees of freedom searching for things you don't know about. So you need to have, you need a couple hundred observations to get started, basically, or else sample splitting, you start running into the law of large numbers, like you just can't do anything. But, I've seen experiments, when I helped run the search engine at Microsoft, we had, tens of millions of observations, but you were looking for small effects, and sometimes that wasn't enough, or you had rare outcomes. So, sample size calculations, it's hard to generalize. But machine learning is going to be helpful relative to pre-specified hypotheses in cases where you have lots of covariates, you don't have strong hypotheses, there might be lots of interaction effects you don't know about, and you have enough signal that you actually are able to both discover things and assess their validity. Let's see, sorry. Methods for discrete treatments. Is that because continuous treatments are particularly difficult? Well, so one of the reasons I started with discrete is that I was trying to bridge the gap between two literatures. One is a literature in econometrics and social sciences and biostatistics that mostly focused on discrete treatments, and then a prediction literature. And it's the easiest thing to do to kind of bridge between, I'm just predicting outcomes, versus I want to predict treated outcomes and control outcomes. So pedagogically and methodologically, that's by far the easiest place to start. And then you can isolate the issues. So a randomized experiment with binary treatment versus a prediction problem, that's the easiest step to take. But actually, a lot of my methods work fine for continuous treatments too. And our GRF package works for continuous treatments. But then there's another set of difficulties that arise if there's heterogeneous treatment effects when you have continuous treatments. So it's really the interpretation of results for continuous treatments either is complicated or it requires more assumptions. Because if you think about the dimensionality, right, if you have a continuous treatment and the marginal benefits of the treatment can have an arbitrary shape and there can be arbitrary heterogeneity, wow, like you're looking at a very high dimensional function. And so what often people will do is put a parametric form on the treatment effect, and then boil it down to a single parameter. And then you can look for heterogeneity in that parameter, or maybe 2 or 3 parameters. And so our GRF package and our GRF paper actually allow for all of that and allow for parameter heterogeneity, however you want to put it in there. But I would say it's more complicated, so I don't usually start there for presentations. But absolutely, that's an area that we're interested in. And in my papers with David Bly on price sensitivities, price is a continuous variable as well. Is there code in Stata? No, we don't have Stata code. We have R stuff, but I have a lot of stuff up there in R. And we try to make it super easy. And I have tutorials out there, and I have video lectures. And so if you have any trouble finding any of that stuff through Google, send me a note and I can send you tutorials. I teach classes that have PhD classes that have more than 60 people in them. And a lot of people don't know R before, and they're still able to use the packages. Just explaining what I mean by causal inference of software systems, that might mean, suppose I have this huge mass of a software system and there's lots of state variables, and I don't have documentation for the software system. I'm trying to figure out whether state variable 1 causes state variable 2, or whether state variable 2 causes state variable 1. If you actually could understand your millions of lines of code, this is a knowable fact, but as a practical matter, you don't know. A similar example would be a biological system. Like I get stressed out and then I sweat and then my skin is wet and then something else happens. I get stressed out and then a hormone comes and that hormone goes and tells me to sweat. So there's some causal pathway in my biological system. We could try to discover that. But there's a true kind of natural dynamic sequencing of things, and we might try to discover how that works. So that makes a lot of sense in a physical system. Whereas if I instead said, let me just take all the data from the census and see whether parents' education causes children's outcomes, or children's labor market outcomes causes parents' education, or whether, I don't know, which city you live in causes this, causes that. Like actually all of these things are related to each other. And so it's kind of a silly exercise to try to discover that from a social science data set, but it makes a lot more sense in a physical system. So I guess we are now 2 minutes over time. So I don't want to make people feel obligated to stay. I'm going to keep, let me just pause a second and say thank you so much for having me here. If the organizers are okay, I can stick around and continue to answer questions via Zoom, but I just really want to thank the audience for coming. Is it all right if I stick around and answer a few more questions?
Absolutely, thank you.
Okay, let's see. So Don asked, can I say more about the procedures by which the quintiles are described? What are we looking for in those descriptions, which assign that we are doing this part correctly or usefully? So I would say it's to start with, it's really a descriptive exercise. We just want to answer a precise question. What are the characteristics of people who have high treatment effects versus the characteristics of people who have low treatment effects? There's not one way to categorize people. So you could come up with some other way to put people into quintiles, and it could be different. But the idea is that if I've used a flexible method like GRF that really flexibly uses all the covariates to figure out, what treatment effects heterogeneity looks like, then hopefully those quintile assignments will be stable. I might split differently. I might be able to get the same thing through a regression or something else, but hopefully whichever method I use and however I split and however I regularize, I end up finding roughly the same people. There are many different ways to get there, but I found them. And so then my question is just, again, what are their characteristics? How are they different? It's a way of describing and interpreting the results. An alternative, which is what we used to do with regressions, is you imagine that you've just got this tau of X function, or like coefficients of a treatment interaction effects in a regression, and you try to interpret the individual partial effects. And that would answer questions like, if I held all of the other characteristics fixed and I changed just one, what would that do to my estimated treatment effect? That's also an interesting question. It's a different question, subtly different. But generally, we're just trying to describe at that point. I think I view it as a descriptive exercise. Another question was, how is the policy estimated and how to measure the uncertainty of the estimation? So my team has been focusing on two different ways to do it. One is to use a non-parametric model, like a forest, put people and then assign people to groups just according to what the non-parametric model says is best. So for each individual, they have 3 estimates: estimate for arm A, estimate for arm B, estimate for arm C. You just take the max. You just stick people in the group that looks the best according to those non-parametric estimates. We use various things like honesty and sample splitting and cross-fitting to make sure that you don't use the same data to put yourself in a group and evaluate things, or you can just hold out a test set to make things completely clean. And then you, as I showed in my slides, you can just look at the difference in means in the test set and you'll know how well you did. The other way is estimating what we call these policy trees. And we do that using an optimization routine that basically just looks for the global solution. What is the best way to divide people into groups according to their estimated treatment effects? So that is a 2-step approach. First, we use a non-parametric model to come up with conditional average treatment effects. And second, we do an optimization routine to try to put people into groups. And that's in our policy tree package in R. Rare outcomes, but large sample. That is a really big question. That's a very common one for tech firms. And you have to make sure that you don't divide your groups too finely. Other than that, you need a big sample. One of the things that I did at Microsoft was I actually used surrogate outcomes. So instead of looking at whether you actually say there was actually a conversion on a click or something, whether a consumer actually bought something, I used a predicted conversion based on intermediate outcomes that I estimated, like how long they spent on the website. And so I have some other papers with Raj Chetty and Hito Imbens and Hyun-Sung Kang about using surrogates. And one of the motivations for that was exactly this rare outcome. I also used that in a paper on enhanced 911 I wrote in the 90s, where mortality was the rare outcome. So invite me back if you want to hear me talk about the surrogate work, which is very applicable for those questions. One other question was companies that provide you data, what have been the most complicated challenges around getting data and implementation of results? So it's much harder than you think, even for sophisticated companies, to get approval for running experiments and to actually instrument and implement experiments. And they do need to be big for small treatment effects. So our partner has had more. We had all these ideas about running adaptive experiments and running bandits and things like that, and the engineering costs were too high. And if you think about it, a firm that's modifying their code that's going to be served to their live customers, if you introduce a bug, that's a disaster. So they have very robust testing protocols for anything that goes out live. And that just puts a tax on what you do. The ideal thing is to find a company that's already experimenting in a certain dimension and they've already debugged all the code to do that testing. And then you're just plugging in different treatments. That goes much faster. And so trying to understand the engineering sophistication of your partner and make sure that your experiments are aligned with things that are low friction versus high friction is a piece of advice that I would have. Let's see. What are the domains of social issues where causal inference can work better and impact better? So I've been focusing a lot on education, but it's harder than you think because you need big sample sizes and a lot of ed tech interventions don't have a lot of highly engaged users. It's also hard to measure the final outcomes you care about. And that's actually been the reason I've done this work on surrogates is because it's so hard to measure the final outcomes you care about. But I remain convinced that, informational interventions are a great opportunity because they're cheap, they're free, we can scale them very easily once we figure out what works. And some of the things our lab is working on now also are misinformation around COVID vaccines, misinformation around elections, spotting fake news. These are things where, in principle, if you can find the right avenue to reach people that's compelling to them, that's going to be helpful. But that's going to be really different because, the concern that, an anti-vax person in Marin County has might be different than the concerns that someone has, in a who has lower levels of education, right? So the kinds of information that you want to give people could be really different in those different cases. Okay, wow, you guys went crazy with the questions. So thank you so much. And look at, I see a lot of people stuck around for all of this. So thanks so much for taking time out of your busy day. And I love the questions. And as I mentioned, we have other streams of research that hit on a lot of these practical questions. So, if people are interested in, chatting again in some other venue, I'm really interested in engaging with other people who are running these experiments. I think we're all kind of on the cutting edge of running large scale field experiments. This is sort of a new thing, and there's lots of best practices that I'm learning every time I run a new experiment. And so I hope that we can have a research community that collaborates on best practices and learnings as we all go along.